Alright, objective 6 of 3.5 is graphing rational functions that we can't use transformations for. So basically we're going to take everything that we've learned dealing with rational functions and we're going to put it together so that we can graph it. Alright, so the first thing we're going to do is we're going to start out with our domain. Now, you don't have to have the domain to graph it, but a lot of times I'll ask you for the domain in it as well, so I'm going to go ahead and put it in this, okay? Alright, so remember your domain, look at your problem. You have a fraction with x in the denominator. So we know that our denominator cannot equal 0. So solve that. So x cannot equal 2. So if you need to, draw yourself a number line, but that means that we can go from negative infinity to positive 2. Not included, union 2 to positive infinity for our domain. The second thing we're going to do is we're going to look for our vertical asymptotes and our holes. I like to do this because domain and vertical asymptote is really closely related. They're both dealing with the denominators, okay? So remember though, before you can do the vertical asymptotes, you need to factor your rational function. And so on this one, my numerator, we can do a greatest common factor of 3. But even when I do that, nothing cancels, okay? So throughout this problem, it's not going to matter if I use the original or I use the factored form. I'm going to get the same answer. Now, if something would have canceled, we'll want to use the factored form from here on out. But for this problem, it doesn't matter. All right, so your vertical asymptote, remember, are the uncanceled factors of the denominator equal to 0. So we do have something still in the denominator. We have that x minus 2. So it's where it's going to be equal to 0. Add 2. And so we find our vertical asymptote is that x equals 2. Now remember, closely related to vertical asymptote are your holes. Holes are the canceled factors of the denominator set equal to 0 and solved. Did anything cancel? Nothing canceled, so there's no holes. Alright, let's keep going. Let's do our horizontal asymptote. Horizontal asymptote has to do with that highest power of x. So where's our highest power of x? Well, it's a little harder to see in the factored form, but the nice thing about the horizontal is it's very kind of forgiving. So even if you use the original one, you're still going to get the same answer as if you use the factored one. So I'm just going to use my original one for this one. Where's my highest power of x? Well, it's both. So remember, that means it's a ratio of their coefficients. So it's going to be y equals the leading coefficient of the numerator, which is 3, over the leading coefficient of the denominator, which is a 1, and 3 over 1 is 3. So our horizontal asymptote is at y equals 3. Now right there near horizontal asymptote is your slant asymptote. Slant asymptote, though, remember, does not exist if there is a horizontal asymptote. Since you said there was a horizontal asymptote, there won't be a slant. The slant asymptote will only exist if the numerator's degree is greater than the denominator's by 1. And in this case, they're the same degree on top and bottom. So therefore, no slant asymptote. Alright, and then something we haven't talked about today, but we have talked about in the past, is x and y intercepts. So we're going to find our x and y intercept. So let's start with our x-intercept. Remember, this is where you set your function equal to 0 and then you solve it. But here's a neat thing about the rational function, guys. If I set, I'm going to do this as a side note, don't write it. So if I set my function, I'm going to use the factored form here, equal to 0 and solve, the first thing I'm going to do is multiply by that denominator to get rid of it. Well, when I do that, I end up with the numerator, and it's always going to still equal 0. So the shortcut for the x-intercept is just set your numerator equal to 0 and solve it. So we have the 3 times the x minus 1 equals 0. So you can distribute the 3 or just divide by it to get rid of it. So x minus 1 equals 0, add the 1, and so x equals 1 is going to be our x-intercept. Alright, then we got our y-intercept. Remember, the y-intercept is where we let x equal 0 and solve for y. And so we got y equals 3 times 0 minus 1 over 0 minus 2. So 3 times negative 1 over negative 2. And so we get y equals negative 3 over negative 2, which is just 3 over 2. So my y-intercept is at 3/2, or you could say 1.5. Alright, so from here, what I do next is I go ahead and I start setting up my graph. I still have some other points I need to find, but I go ahead and set up my graph at this point. So I'm going to borrow the room for pencil problem number 6 over here. You can do this below, but I can't. And I'm going to start setting up my graph. Alright, and so I think if on our marks, if we do 5 each way, we'll have just about enough. And so we're going to graph what they've given us, okay? So we don't need the domain to graph it, but we do have a vertical asymptote at x equals 2. So I'm going to go to x equals 2, and I'm going to draw in that vertical asymptote. So remember, it's a dashed line. So that way we know it's not really part of our graph. It's just there to help us shape our graph, okay? We don't have any holes. If we did, we would just draw open circles at those ordered pairs. We have a horizontal asymptote at y equals 3. No slant asymptote. We have an x-intercept at x equals 1. And we have a y-intercept at 3/2, or 1.5. Alright, now I need a few more points to help me graph this. I can kind of see probably on the left side of my vertical asymptote where my graph would be, but on the right side I don't know if it's going to be above or below that horizontal asymptote. So I'm going to create an interval table. Different people do it different ways. If you watch another video, they might do like a number line, okay? But I go ahead and do the interval table because we use it in the next lesson as well. And so that way we're already kind of familiar with it, and I add just an extra column or two to it there. Alright, so for my interval table, so let's see. Let's say our graph is our 8, and so our interval table will be our 9th step. So we're going to have our interval. We're going to have an x value and a y value. And this is the x and y value will give me an ordered pair in which I can graph, okay? Now I'm going to need some room to work, so I am going to erase some of this that I have over here on the left side. We've already graphed it, so I don't need it. But I do need some room to show my work so that y'all can see where I'm getting my answers from. Alright. Alright, so our intervals. The intervals here are going to be created by your x-intercepts and your vertical asymptotes. So really you just kind of look at your x-axis to see what's going on here. And so my interval always starts at negative infinity, and I can see the first thing that I have going on my x-axis is that x-intercept right there. So I'm going to go to negative infinity to that x-intercept, which is at positive 1. So negative infinity to positive 1. I need to pick an x value that's in there. Well, typically we love 0, but 0's already there, so it's not going to really help me any. So let's pick a different one. So let's try like negative 1. So over here in my work, I'm going to go plug negative 1 into my function. So my y value is going to equal the 3 times the x minus 1, but now x is negative 1, over x minus 2, but x is negative 1. And so I'm going to work this out. And I got 2. So I have the ordered pair negative 1, 2. I'm going to go graph that point. Now, so we just covered, don't draw this in, we just covered that interval. My next thing that's going on my x-axis is I have an interval between that x-intercept and that vertical asymptote, so between 1 and 2. So my next interval then is going to be from 1 to 2. And so I need to pick a number in there. So I'm just going to pick 1.5. And so I'm going to come over here to my work and I'm going to do the same thing, but this time I'm going to plug in 1.5 for x. And I'm going to work this out. And I got -3 for my y value. And so 1.5, -3, I'm going to plot that point. Now, on the other side of my vertical asymptote, I can see I'm going from a vertical asymptote, so there is nothing. So it's going to go from that vertical asymptote at 2 all the way to positive infinity. So I'm going to pick a number in here. So I'm going to pick maybe like, let's do 4. Alright, so I'm going to plug in 4 now for x. And so I ended up with 4.5. And so I'm going to plot that point, 4 and 4.5. Now, I can pick more points on that side if I want to, so I have more points to connect. But the whole thing I needed there was what kind of, not really quadrant, but if you look at our vertical asymptotes as if they split it up into quadrants, we need to know which part to graph that other piece in. And so we know now that this piece here is going to be up here. So we're just going to let it be shaped by our asymptotes for that part. And then the other, to the left side of that vertical asymptote, we have a bunch of points there. We can just play connect the dot and then shape it by the asymptotes. And so there is the graph of our function. Alright, so let's try it again on pencil problem 6a. This is going to take some practice. So if you need to, pause this. First thing I want you to do is go through and find your domain, your vertical asymptote, and your holes. Okay, go through, look at solved problem, go through it and see the steps so you can try to do it. And then check it. Alright, so for domain. Domain is the denominator cannot equal 0. So x cannot equal -1, which means we're going to go from -infinity to -1, union -1 to infinity. Vertical asymptotes. So we need to see, can we cancel anything? We cannot. No factoring. So my vertical asymptote is the uncanceled factors of the denominator equal to 0. So we have a vertical asymptote at x equals -1. Did we have any holes? Nothing canceled, so there's no holes. Horizontal asymptote. Remember, that's where our highest power of x is. It's on both, so it's a ratio of their coefficients. So it's -1 over 1. So let's see, it says -1 over 1, which would be -1. So we get y equals -1. Slant asymptote, the numerator is not greater than the denominator by 1, so it's none. Remember, you can't have a slant and a horizontal. Since we have a horizontal, there can't be a slant. Okay, Xintercept. The shortcuts is set the numerator equal to 0 and solve. So divide by the -1, and we still get x equals 0. And then the y-intercept. The y-intercept is where we let x equal 0. Solve for y. So we got -0 over 0 plus 1. -0 is just 0 over 1, which is 0. So we have a y-intercept at 0. And then we're going to go graph those pieces. Try that again. I can draw a straighter line than that. Well, trying to make it a little more level. Alright, that's better. Alright, so let's graph what they told us. They said, it says we have a vertical asymptote at -1. No holes. We have a horizontal asymptote at -1. No slant asymptote. X-intercept and Y-intercept at 0. Alright, so we got to graph this. So let's see. Let's make our table. So we're going to have our interval, our X value, and our Y value. So our interval is always going to start at -infinity. And remember, go across your X-axis. The first thing we have is I go across this X-axis right here is I see I have a vertical asymptote at -1. So between -infinity and -1, I'm just going to pick -2. Let's go plug -2 in. So we get y equals, that's a negative x, so -2 over x plus 1, so -2 plus 1. So -2 is 2 over -2 plus 1 is -1, and so I got -2. So I have the ordered pair, -2, -2. Okay. Keep going to the right from the vertical asymptote of -1. The next thing I see is my x-intercept is 0. So from -1 to 0, so I'm going to pick like -0.5, plug it in. So I got 0.5 over 0.5, which is 1. So at -0.5, we're up at 1. And then after that x-intercept, I don't have anything else, so I'm going to go to positive infinity. So from the x-intercept is 0 to positive infinity. And so we can pick like maybe 2. So let's plug in 2. So I'm going to do that over here. So I have a -2 over 2 plus 1. So -2 over 3, so we get -2/3. Oops, what was the -0.5? 1? I didn't actually write it in there. Alright, so 2 and -2/3. So I can see on the left side of the vertical asymptote, I have that single dot on the bottom left. So I'm just going to draw in my graph and shape it by those asymptotes. And then on the right side of that vertical asymptote, I can see those 3 points. I can just connect the dot and shape them by those by those asymptotes. And so there is our graph. Okay, moving on along then. (6b) wants us to graph this. So we're going to do the same thing. So first thing let's do is let's find our domain. I'll change colors. I used all blue in that last problem. Okay, so the domain, I see I have a fraction with x in the denominator. So I know that x squared plus 2 cannot equal 0. So solve for x. X squared cannot equal negative 2. Take the square root. X cannot equal plus or minus I square root of 2. So therefore, we know that there's no restriction for our domain, so it's negative infinity to infinity. Okay, so for vertical asymptotes, we need to factor if we can. Nothing factors, nothing cancels. So it's going to be our denominator, uncancelled factor of the denominator equal to 0. Well, that's the same as this one. So we know the only difference is it's not the not equals. So we're going to end up with x equals plus or minus I square root of 2. Again, remember vertical asymptote with an I just means that there's not going to be a vertical asymptote. All right. Were there any holes? Did anything cancel? Nothing canceled, so there's no holes either. Horizontal asymptote. Where is that highest power of x? So on this one, x to the fourth is in the numerator. So if I use no to help me, excuse me, if I use no to help me, remember the n stands for none. So if we don't have a horizontal asymptote, we got to think about that slant asymptote. The slant asymptote says the numerator, the degree of the numerator has to be greater than the degree of the denominator by 1. Well, is the degree of the numerator greater than the denominator? Yes. X to the fourth is greater than x squared. Is it by 1? No. So therefore, there's no slant asymptote either. All right. Xintercept. Remember, Xintercept, the shortcut is set the numerator equal to 0 and solve. So x to the fourth equals 0. We can take the fourth root of both sides, and we still get x equals 0. And then our y-intercept, plug in x is 0, solve for y. So we get y equals 0 to the fourth over 0 squared plus 2. So 0 over 0 plus 2, so 0 over 2, which is 0. So our y-intercept is y equals 0. Trying to see if I missed something, because I thought I should, maybe my steps are off. Did I forget something? Not that I know of. Alright, so if I did, I'll realize it in a few minutes. So I'm going to borrow the room over here so that we can graph it, not with that. Okay. Alright, so let's see. No vertical asymptote. No holes, no horizontal asymptote, no slant asymptote. X-intercept and y-intercept are both at 0. Okay. So when I go to do my interval table, I'm going to take off a little bit of this so I have some room. Alright, so my interval, x value, and the y value. Alright, so my interval is always going to start at negative infinity. And if I look at only thing I have on here is my x-intercept. So it's negative infinity to 0. So I'm going to pick, like, let's say negative 2. We're going to plug negative 2 into our function here. So I'm going to have to erase some to give myself some room to work. Alright. So y equals negative 2 to the 4th over negative 2 squared plus 2. So negative 2 to the 4th is 16 over 4 plus 2. So 16 over 6, which is what, 8 over 3. So what is that? 2.7 approximately. So negative 2 and 2.7, so somewhere in here. And then I don't have anything else on my x-axis, so we're just going to go 0 to infinity. And so I'm going to pick positive 2. So 16 over 4 plus 2, looking really familiar, right? 16 over 6, which we already said is approximately 2.7. Alright, I don't have any asymptotes, anything like that to shape this, so we're just playing connect the dot here. So it's just going to do something like this. What does that look like? It looks like a parabola, and that's what it is. If you take x to the 4th divided by x squared, you get an x squared. Okay, so therefore our graph is quadratic. Alright, let's try 6b. Here, pencil problem. Alright, so our domain. Now I'm going to do this. I'm going to put that negative 1 up there on top. Okay, so our domain. Our denominator cannot equal 0. So x squared minus 4 cannot equal 0. If I move the 4 over, x squared cannot equal positive 4. Take the square root, x cannot equal plus or minus 2. So that means we're going to go from negative infinity to negative 2. Negative 2 to positive 2, and then positive 2 to infinity for our domain. Vertical asymptotes. Well, now we need to make sure we factor this out. So negative 1 over x plus 2x minus 2. Does anything cancel? No, so our vertical asymptote is our denominator equal to uncanceled factors of the denominator equal to 0. And so we know x plus 2 would equal 0 and x minus 2 equals 0. So we have a vertical asymptote at negative 2 and at positive 2. So x equals negative 2 and x equals positive 2. Do we have any holes? Well, did anything cancel? It did not, so there's none. Horizontal asymptote. Where is our highest power of x? Well, the factored form's a little harder to see, but remember I said you could always use the original form. So our highest power of x is in the denominator. It's x squared. And since it's in the denominator, I'm going to use no to help me. What did that O stand for? Remember, that was the y equals 0. Alright, slant asymptote. The degree of the numerator has to be greater than the degree of the denominator by 1. Is the degree of the numerator greater? It is not, so therefore there's none. Alright, so then x-intercept. That's where we set our numerator equal to 0. Our numerator was a negative 1 equal to 0. Does that make sense? No, there's no x, which means there's no x-intercept. Y-intercept, plug in 0 for x and solve for y. So negative 1 over. And it doesn't matter if I use the x squared minus 4 or the x plus 2x minus 2 because nothing canceled. I'm going to use the x squared minus 4. It's just a little easier, I think. So we get negative 1 over 0 minus 4. So negative 1 over negative 4, so 1/4. Alright, and then we're ready to graph. So I'm going to borrow this other room over here next to it so I can graph there. Alright. Borrow a little room down here again for my table. And I'm going to cut off part of this so I have room to show my work. Alright, so I got my interval, my x value, and my y value. Alright, so, oh, I didn't graph all that before I cut it off. I gotta go back and get it. Sorry guys, I don't have it memorized. Alright, sorry, I got a little ahead of myself. Okay, vertical asymptote it. X equals -2 and x equals +2. No holes, vertical asymptote at y equals 0. No slant asymptote. No x-intercept, no y-intercept at 1/4. Alright, so now I'm going to cut off part of this. Now that I've got this graphed. Alright, so I got my interval, my x value, and my y value. Alright, so my interval, the only thing I have on that x-axis are those two vertical asymptotes. So my first interval is going to be from -infinity to the first vertical asymptote. So -infinity to -2. So I'm going to pick maybe like -3. Let's plug -3 into our function. So y equals -1 over. Now I can use the factored form, or I can use the one I put in red there. I'm going to use the one in red. I think it's just easier. But you could use either one of them because nothing canceled, so it's not going to matter. And we said we're going to plug in -3 minus 4. Okay. So we get -1 over 9 minus 4. So we get -1/5. Alright, between -2 and +2, because that's my next thing that affects my x-intercept. Now 0's already got 1, so what if we put, let's do -1. So we get 1/3. And that's hard, but remember 1/3 is bigger than 1/4, so it's got to be a little bit up. And I know it looks like ours is almost up at the 1, but it is what it is. Now this one's a little weird because we don't have that x-intercept. So that means we're not going to cross that x-axis. So I'm going to throw in an extra point because I need to know kind of what's happening over here just to make sure, okay? Because I can't cross, so I believe I'm going to go back up, but let's verify it. So, well, yeah, so what if I also tried +1? It's in the same interval, okay? But just so we can see what's going to happen. So if I plug in +1, we can see it is the same, so therefore we know we're going to get 1/3. So it is going to be a little parabola shape going on here. Okay. And then we have the other side of that last vertical asymptote, so from 2 to infinity. So let's pick +3. This looks familiar too, doesn't it? So we got negative 1/5. So 3 and negative 1/5. Alright, so starting on the left, just over here in this area, I've got that one little point. So I'm going to draw coming out of that point and just shape it by those asymptotes. As I go to the left, it's got to be shaped by that one. So remember, it's going to get closer to it, but it's not going to touch it. And as we go to the right, it's going to be shaped by that other asymptote. We already kind of said here in the middle, it's going to be kind of quadratic looking. So we know it's going to have to go up, and it's going to be shaped by that vertical asymptote on both sides. And then on the far right, we got that single point there. What's going to kind of look like what it did on the left, okay? Single point, we're just going to draw going to the left and shape it by that vertical asymptote. Draw going to the right, and it's shaped by the horizontal asymptote there. And so that is the graph of our function.